Good evening.
Good evening, sir.
Good evening, Professor.
Why?
Good evening, sir.
I think very few people have joined, or
From our batch, around 8 people are joined. Maybe let me check, sir. Further people from my batch.
let's wait for a couple of more minutes to see if others come. Okay.
Right, sir. Right, sir. Hello.
Yes.
Sir, actually, I have told earlier that assignment number 1, I have submitted wrong assignment. Then it is not possible to upload the same link. Then I informed you and send the assignment in separate mail to you, but it was not considered till now. They
Is
marked
it?
as,
Okay,
yeah,
I will look into it.
so they marked as a non-availability of.
I will change it. Yeah.
Yeah. Thank you, sir.
Can you remind me, send another email to just now?
Yeah, sir. I will send, sir.
I think let's get started. I think it's more than 10 minutes. So until, as we have discussed yesterday, until yesterday we have looked at constant amplitude loading, and in today's class we will look at what happens if you have the amplitude of loading is also variable. So we have made a case for that. Sometimes the variable amplitude of loading may be different, correct? So let us see what happens in such scenario in today's class. Okay, so if you look at this figure, so you can see now what do I mean by variable amplitude loading. Let us say the loading history for some cycles, say N1 cycles, has an amplitude of sigma A1. For an N2 cycles, it has an amplitude of sigma A2. For N3 cycles, it has an amplitude of sigma A3. And keep in mind that in all these cases, mean stress remains the constant. In this case, it is fully reversed loading. The mean stress is 0. All right. So now, how do I go about finding the life of the component? So the idea is that in the SN diagram, if you look at this, if you are operating at sigma A1, that some, let us say sigma A2 is the smallest stress amplitude. If you are operating at sigma A2, the number of cycles to failure at when you operate at sigma A2 is, let us say, NF2. Okay. Similarly, if you are operating at sigma A1, the number of cycles to failure is NF1. If you are operating at sigma A3, the number of cycles to failure is NF3. All right, this is coming from the SN diagram. But instead of at sigma A1, you are not running for NF1 cycles, but you are only running for N1 cycles. That means only a fraction of the total number of cycles at which the failure happens. So this, you are operating in N1 cycles, but at that particular stress amplitude, if you run for NF1 cycles, the failure will happen. So the fraction of life that is consumed is N1 by NF1. All right. So then you have variable amplitude loading, the fraction of the life consumed for a given sigma A1 is N1 by NF1. And if you have such variable amplitudes, the requirement is that the sum total of all these fractions cannot be greater than 1, because that is the total life available. So that rule is what we call Palmgren-Minor rule. So if you are operating at sigma A1 cycles, corresponding to sigma A1, the failure number of cycles to failure is NF1, but you are only running up to N1 cycles, which is less than NF1, right? So N1 by NF1 plus N2 by NF2 up to as many number of cycles, sum total should be equal to 1. So sigma Nj by Nfj or Ni by Nfi equal to 1 is your Palmgren-Minor rule. Is that clear? So this is the fractional life. So sum total of all the fractional lives must be equal to 1. That is, total fraction cannot be more than 100%. Okay.
Professor, how to see that NF1 in the graph? How to interpret it numerically?
Because for this is a material. For this material, you will have a SN diagram, right? This is SN diagram, isn't it? S is nothing but our stress amplitude. So I am writing, instead of SN, I am writing sigma A, that's all. For this material, this is the SN diagram. If you know the SN diagram, if you are operating, if your component is subjected to this kind of a stress cycling, then if you are operating at sigma A1, if you plug in sigma A1 in place of S, then you will calculate N, that is corresponding to the number of cycles for failure. At sigma A1, if this is your curve for that material, at sigma A1, your available life is NF1 cycles. Correct?
Okay, Professor. Then what about N1, N2, N3, those things?
So at sigma A1, you can operate at sigma A1 up to NF1 cycles before the material can fail. That is what this tells you. This diagram tells you. Correct? but you are not operating up to NF1 cycles, but you are only operating up to N1 cycles where N1 is less than NF1. In all these
Understood.
cases, each fraction should be less than 1.
Understood, Professor. Thanks.
Okay. If you are only operating for N1 cycles, that means you have only consumed a fraction of the life that the machine can, the component can give. Right? The idea is a sum total of all these lives cannot be more than 1, and hence N1 by NF1 plus N2 by NF2, all of them will be equal to 1. If you have only one single stress amplitude, N1 by NF1 is equal to 1, meaning only when N1 equal to NF1 and 100% life will be consumed. Otherwise, you will still have some life left. That's what it means. Okay.
Yes, sir. Yeah, thanks.
Sir, here the mean is same for all the small cycles.
That is what here, right? Here there is no mean stress effect.
If the mean changes,
Yeah. Now, what is the way? You tell me.
I'll calculate for each and every.
You can calculate, for example, for this combination of mean stress and sigma A1, you can calculate the number of cycles to failure or not.
Yes.
Like yesterday we have calculated. And instead of directly calculating, so let me show you how do we go about doing it, right? Because you need to understand that. So let us say the first cycle right? That is your first one. Let me okay. The next cycle is like that. So for this particular thing, sigma m is equal to 0. For this particular thing, this is my sigma m. So let us say sigma m1 is equal to 0. This is sigma a1. And for this, sigma a2. And that is my sigma m2. Correct? So let us say this is run for n1 cycles. And that is run for n2 cycles. Then when I am calculating n1 by nf1, this nf1 corresponds to a scenario sigma m1 equal to 0, sigma m equal to 0, sigma a is equal to sigma a1. Corresponding to that, what is my nf? This letter n2 by nf2, where nf2 corresponds to sigma m is equal to sigma m2, sigma a is equal to sigma a2. Corresponding to this value, so how do I do that? I go sigma m, sigma a curve, and here I identify this is my sigma m2, sigma a2. So then, and let us say that is my sigma SUT. Then I draw a line connecting these two fellows, and then I get my SF, correct? Corresponding to this SF, I will calculate, I am calling it as SF2. Then corresponding to SF2, I will calculate my NF. Right? And because it is the same material, whatever formula that I am using here in order to calculate NF1, I make S is equal to A n power B. A and B are fixed. It is the same material. So I will calculate NF1 is equal to sigma A1 by A whole to the power 1 by B. Right? Similarly, NF2 will be SF2, whatever I computed, by A whole power 1 by B. Because this is taking, because this point and this point is going to have the same life. Once having done that, now my equation will be N1 by NF1 plus N2 by NF2 must be equal to 1. Right?
Got it, sir. Got it.
Yeah. Yeah. All right. So once that is clear to us, then we can go about understanding how to go up solving. So it is again, when you are applying variable amplitude loading, a particular sequence of loading may be repeatedly applied, meaning you have sigma A1 and then it goes from sigma A1 to sigma A2, and again it will again have sigma A1, sigma A2, again sigma A1, sigma A2. So that means there are n1 cycles of sigma A1, n2 cycles of sigma A2. So from here to here it will go, and again it will start going here. So that means you have, in this guy, here you have some value from here to here it went up, and at that level you have sigma A1 corresponding to some mean stress like we have discussed. And then corresponding to this sigma A2 there is some mean stress, right? And there is also another one where there is a larger cycle from here to here and then coming here, right? So these, that means there is one cycle that goes from, you can see that this value to that value, that is one cycle. And there are n1 cycles between sigma A1 and sigma M1, n2 cycles between sigma A2 sigma M2, and this one will be sigma M3, as you can see, right? This is the mean stress of this larger cycle. So that is one cycle every time. So what is happening is one large cycle and two small cycles are repeating. So that is what I am calling as, this is N1 cycles, N1 by NF1 plus N2 by NF2 plus 1 by NF3. What is NF3? NF3 is corresponding to this larger stress amplitude. Is that clear? But there is only one cycle within this. And such cycles will be repeated, say, BF times. BF is the number of times that this cycle is repeated. All that sum should be equal to 1. This is because in many machine components, for example, if you take an aircraft undergoes a takeoff. So that is actually a larger load. You takes off, and it, after having initial takeoff, before once it takes off from the land, and then before it goes to cruising altitude, it goes through higher, because it has to go through the what you call clouds and all. So it may be experiencing higher load. So that maybe you can see that pre-cruise scenario, right, or cruising scenario, and then again it is landing. Again, that time it will have what you call higher loads coming down, and then it will have taxiing. This may be a taxiing load. And this happens at each every takeoff, landing, taxiing, takeoff, landing, and taxiing. Correct? So this is one example of an aircraft, but you can also have, for example, if you are having a machine component initially started, so that will have more load, and then it is operating condition, and then it is actually cooling down. Before completely stopping the machine, you first reduce the load, and then such a smaller load you operate for some time, and eventually you continue this operation, right? So this is typically what happens in several machine components, and hence you have defined a number of repetition cycles. So this N1, N2, and 1 cycle keeps on repeating. So the question is, how many such repetitions can you have? Is the question that we need to answer. Is that clear?
Yes, sir.
Yeah. Okay. All right now. So now let us solve this problem. Please, can you please look at this particular question? And he has given a n power b, a is given, b is given, a is 1643, b is minus 0.0977 for this particular material. We need to find out how many repetitions are required to cause fatigue failure. I think we have discussed enough. Now I would like you to get started and then look at solve the problem.
Sir, around it comes 71,000, sir.
So, are you working or what is the status?
Sir, it comes approximately 71,000, sir.
How many repetitions?
Around 71,000, sir.
71%. Repetitions
1000,
we
sir.
have to calculate, no? The number of repetitions that we need to calculate. That is, see, if you look at the previous slide, in that you have N1 and 1 by NF1. That is what we have, right?
Sir, 72,000 it is coming, sir. 72,000 repetition is coming, sir.
72 repetitions, okay.
Hmm.
Good. So how do we go about doing? So here, if we not solve the problem, let us try to solve the problem. Okay. So this is the thing, right? That we are having. So now, what is sigma A1? Let us say that is our first cycle. These are how many cycles? 1, 2, 3, 10 cycles, right? So sigma A1 is how much? 400?
290.
It is 0, no? I am talking about this cycle.
Okay.
Sigma M1 is 400, right? And N1 is 1 cycle. Sigma A2 is how much?
That is 290.
What is sigma M2? Sigma A2 is 800 minus 220 by 2. Isn't it? That is 580 by 2. That is 290. Sigma M2 is 800 plus 220 by 2. That is equal to
510.
1020 by 2. That is 510. Right? And N2 is 10 cycle. All right. Now the question is BF, number of repetitions, 1 by NF1 plus N2 is 10 by NF2 is equal to 1. So we need to find out what is NF1, what is NF2. Right. So now let us look at what is the ultimate strength of the material. SUT is 1172 MPa. From the Goodman diagram, what you can write? Sigma M by SUT plus sigma A by SF is equal to 1. Correct? So we need to find out in the Goodman diagram. Let us say this is my sigma M comma sigma A, and that is what I need to find out. And corresponding to this, let us say number of cycles to failure is NF1. So that is sigma M1 comma sigma A1. Right? And corresponding to that, that will be my SF1. Sigma M1 by SUT, sigma A1 by SF1 is equal to 1 is what we have. So can you calculate SF1? What is sigma M1 by the way? 400. Isn't it? Sigma M1, first one we are considering this, isn't it? That is the first scenario. So I am plugging in this equation. Therefore, sigma m1 is 400 by 1172 plus 400 by, sorry, SF1 is equal to 1. That implies SF1 is equal to 400 by 1 minus 400 by 1172. What is that value? This is 772, right? So what is SF1 into 1172? Is this clear? How am I doing this? Is there any questions here? How am I doing this? I am assuming everyone is understanding, okay? If you don't understand, you have to speak out.
607.25.
Those of you who have solved, they should be able to answer, no? What is the number? .25. That is SF1. So, because it's the same material, it is governed by S is equal to n power b, that is 1643 times n power j minus 0.097. So, NF1 is equal to SF1 by 1643 whole to the power minus 1 by 0.097. 0.977. That is equal to 607.25 divided by 1643 whole to the power minus 1 by 0.0977. What will that be?
$26,574.
Sorry?
26,574.
That is NF1. Now coming to the second scenario. What is second scenario here? Sigma A2 is equal to 290. Sigma M2 is equal to 510. Correct? Copy. For this, I need to find out, corresponding to this, I need to find out what is SF2. What is the meaning of that? So here sigma M1 was 400, 400, right? I am talking about another line which is sigma M2 is 510. So that is somewhere here. And sigma A2 is so I am talking about somewhere here, and then I am talking about another line. Right? And that is my SF1. So I need to find out SF2. That is my SF. So again, I follow sigma M2 by SUT plus sigma A2 by SF2 is equal to 1. That implies 290 by 1172 plus, 510 by 1172 plus 290 by SF2 equal to 1. That implies SF2 is equal to 1 minus 510 by 1172. So 290 by that. So that is equal to 290 into 1172 divided by 1172 minus 510.
513.41.
513.41. Oh, it is smaller than that. Huh? The previous one, smaller than the previous
I'm
one.
getting 677.687.
Yeah, it should be larger than that, no? Because
Yeah.
if it is 400, 400, 510 will be outside, no? So it should be larger. So this number is how much?
677.687.
Do you agree? Whoever said 517?
I'm checking, sir.
$662.
I am getting 513 only, sir.
Sir, 513
Yes,
only,
sir.
sir.
The
Previous
5
one may be wrong.
correct. 513.4 only I'm also getting.
I'm also getting 513 only. Did I make a mistake? 513.4 MPa. That's okay. Yeah. Okay, fine. 513.4 MPa. Maybe it could be here, no? It could also be, it need not be outside. Right? The point could be here or here. It depends on where the point is. Right? Anyway, so 513.4 MPa. Therefore, NF2 is equal to SF2 by 1643 whole to the power minus 1 by 0.0977. That is equal to 513.4 divided by 1643 minus 1 by 0.0977. What is the number of cycles to fill?
Uh, 1.48 into 10 power 5 cycles.
1.48
Or
into.
10 power 5 cycles.
So now the formula that we have is number of repetitions times 1 by NF1 plus 10 by NF2 is equal to 1, right? That implies number of repetitions we need to find out. 1 by NF1 is what? 26,574 plus 10 by 1.48 into 10 power 5 is equal to 1. That implies BF, what is this value? BF is equal to number of repetitions is equal to 1 by 26574 plus 1 by 1.48 into 10 power 4. Approximately how many repetitions? Two, 6,574.
9506 cycles.
How many?
I got 9505.
The cycle 9,505.8 because it is the number of cycles. So we should say 9,505 cycles. We cannot say 9,506. You cannot round up here, right? Isn't it?
Yes, yes.
Is this what earlier you got, or you got something else? Someone else gave answer.
Sir, is it times, sir? 9505 times, right? It's not like that.
Repetitions. Sorry, not repetitions. Sorry.
Oh, oh.
Repetitions. Thank you. Yeah.
Yes.
Is that clear? The process is clear to all of you?
Yes, sir.
Right, I don't have the answer to this question, but that must be the right answer. Okay. Now, you have variable amplitude loading, but this variable amplitude loading that we have seen until now is in a very nice way. There is one large amplitude and small amplitude and so on. But sometimes you have the loading happening in a very haphazard manner, very random manner. Okay. In such cases, we employ, how do we count the cycles? There is a method proposed by Professor Endo in 1968 that is called a rainflow counting cycle. So how do we go about this? So if you have a irregular loading cycle like this, here you have peaks A, C, G, I, all of them are peaks. B, D, F, H, J are your valleys. Okay. Now you will count a cycle to have completed when, suppose if you are seeing this X, Y, Z, if the amplitude or stress range is 2 times the amplitude, isn't it? So that means sigma X minus sigma Y, sigma Y, Z minus sigma Y, right? Or delta sigma is the stress range. If the delta sigma of the next signal is less than the previous signal, for example, delta sigma YZ here is less than delta sigma XY, then you don't count it as a cycle. You will count a cycle only when delta sigma YZ is larger than or equal to delta sigma XY. Then you say that there is an XY cycle that happened. Okay, otherwise you don't count the cycle. Okay, and of course, mean and range, you know how to compute that. Now let us look at the scenario. How do you go about counting the cycles, right? So if you see, look at this particular history, right? Let us carefully go through. This is the history. A, B, C, D, E, F, G, H, I. In order to first start counting, we will identify a repetition. Okay. Imagine you are only I is same as A. And if you say I is same as A, then again B, C, D, they are repeating. Correct? So one of the things is you try to look at the maximum peak, and that is where you start. And then I have started at D and then I have ended at D. Right? This is the thing that keeps on repeating. Now let us look at DE and EF. Is EF larger than DE?
No, sir.
No. So that means we don't count a cycle. Now then you leave it. Then come to EF and FG. Is FG larger than EF?
Yes, sir.
Since FG is larger than EF, then you will count a cycle for EF. Once you count a cycle for EF, EF will go away. And you count a cycle for EF and EF will go away, and then you connect D and G. So now you have counted one cycle for EF, right? EF cycle is counted and EF range is what? 1, 2, 3, 4 and mean is 1 because EF mean is 1. And then the new thing is D, G, H, A, B, C, D. That is the new one that you are looking at. Now let us look at it. D, G, H, A, B, C, D. D, G, G, H. G, H is smaller than D, G. So I cannot count the cycle, isn't it? Yes or no? GH is smaller than DG, so I cannot count DG as a cycle. HA is smaller than GH, so I cannot count the cycle. Right? But BC is larger than AB. AB is smaller than HA, I cannot count the cycle. Now I have AB and BC. BC is larger than AB. Since BC is larger than AB, then I can count cycle AB. All right. So I have counted cycle AB, and then AB will go away, and then whatever you will remain is DG HCD. That's what you will have. Now let us look at DGHCD. Again, I cannot count DG is larger than GH, it does not work. GH is larger than HC, does not work. But DC is larger than HC. So I can count HC cycle. When I count HC cycle, that will H will go away, and whatever is remaining DGD. And DG is equal to GD, so I can count one more cycle. So here I have counted first cycle to be EF, second cycle to be AB, third cycle to be HC, fourth cycle to be DG. Now you have variable amplitude mean loading, and now we need to compute whether this will result in failure or not by looking at NF1, NF2, NF3, NF4, because each one of them have only one cycle. Is that clear? Is there any question here? Okay. If
Sir,
there are
is
no
it,
questions,
one
Yeah.
question, sir, actually, is
Yeah.
it different from the rain flow counting method, sir, or it is?
This is rain flow counting. That is what I said. This is called rain flow counting.
Okay.
So now I would like you to use the rain flow counting and then try to answer this question. Again, I want you to find out the number of repetitions required. Okay? I'll give you 5 minutes time. It is very similar to the last one. Any luck? So if you carefully look at this figure, right, it's a variable amplitude loading. Here you have started at A, right? And AB, let us call this as 1. This is A, also 1, 1, 1, and 1, 2 are having same height. So that means this cycle can be counted, right? Similarly, then once this cycle is counted, this is gone. And you start here, again, this cycle is counted, this is gone. Again, this cycle is counted, this is gone. So how many cycles are there? 3 such cycles are counted. All right. And then you have gone from here to here. This 4C is larger than C1. So this cannot be counted. But C1 and 1, 2 are same. So this is counted, this is counted. How many such things are there? 100 such things are there. That means this is done 100 times. After doing 100 times, you will have only 4C, E, F, right? And because all these are counted, so you will go from 4 to E. And then this guy is same as this guy. So that means 4E, E and EA dash are same. And hence this can be counted as one cycle. Right? So now you have, this is first one, sigma M1 and sigma A1. How many cycles are there? 3 cycles. Sigma A2, sigma M2, how many cycles? 100 cycles. And then sigma M3 and sigma A3 for this large one, 1 cycle. And that is what we need to do. So AB, this equivalent to AB, you have to count 3 cycles. CD, C and D, 100 cycles. And then EA.
Sir,
Right?
one question
Yeah.
here, sir.
Yeah.
From A to B, there are 4 numbers are there. We are counting 3 cycles actually.
Because this is 1 cycle, no? AB and BA are equal. So that is 1 cycle, isn't it?
And similarly, the next one we have 100 numbers. We should consider 99 cycles, sir.
No, because it is starting, you see the numbering,
Okay.
right? Yeah, it starts
Okay.
here. Yeah.
Okay.
If you do that, then it will be 101, no? Yeah. Here, if you see peaks, 1, 2, 3, 3 peaks. Here, similarly, you have 100 peaks, right? 3 cycles, 100 cycles. So A to E, 1 cycle. And you have sigma min, sigma max. And please note that in these 2 cases, sigma min is negative. In such scenario, what you will do, as we have discussed, sigma min should be considered 0. Using that, you can do that, or you can, this is sigma max and this is sigma min. And what will be, if you do that, sigma min, if you take, sigma A will be 350, right? And corresponding to that, you have mean sigma M should be taken as 0. If you take sigma min to be 0, and then accordingly you have to calculate NFJ, and you have calculated N1 here will be 3. So Nj will be 3 by NFJ, that will be this number. 100 by this number is this, and 1 by this number is that, right? And that gives you this thing, and then from there you can calculate number of repetitions. 3259 repetitions. This number may vary depending upon how you are computing NF1, NF2, NF3. Whether you are taking sigma min to be negative or positive. So this is one formula that is also available in the literature, which, excuse me, when you have mean stress, you can also use this formula. But I would like you to follow the approach that we have used, and then accordingly calculate NF1, NF2, NF3. That may be different. Okay, it may be different than what you are getting here, and then compute the number of repetitions. Okay. Is there a question? Any question here? Okay. There are no further questions. Now let us move on to, so far we have not accounted for the presence of notches when you are doing the fatigue loading. Now we will look at the effect of presence of notches in fatigue loading. Okay, this is the introduction that I have already spoken about. And wherever you can find notches, is like this turbine blades and all, you can see notches, and which are usually subjected to fatigue loads. And we have discussed in the static loading scenario, the theoretical stress concentration factor KT is actual stress divided by the nominal stress. Nominal stress means far field stress. That is your stress concentration factor. And for a different, for example, an elliptic hole, we have 1 plus 2 A by C is your theoretical stress concentration factor. And so the actual stress will be KT times sigma nominal that we have learned. And this is how we get KT, theoretical stress concentration factor, which we have, I'm repeating whatever we have done in the static loading scenario for different geometries. But what happens when you have a notch? If you have an unnotched specimen, this is how, if there is no notch, if you have a circular shaft, simply, then if you have a circular notch, you simply have, this is the stress SN diagram. You simply multiply that with KT. This value, if you multiply the stress amplitude with KT, divided the stress amplitude with KT, then this will be your stress life diagram. If you divide this with KT, theoretical stress concentration factor, by 3.05 in this particular scenario, this is the actual one. But when you do the experiment, what you find is the life, that fatigue life that you would compute in the presence of a notch is actually going to be higher than what you would predict using theoretical stress concentration factor. That means when you consider fatigue life, you cannot use theoretical stress concentration factor, because the stress concentration factor is actually, in the case of fatigue, is lower than the static scenario, which is counterintuitive, isn't it? Fatigue is supposed to be more severe, but it is here, fatigue, under fatigue loading, the component is having a lower stress concentration factor. Fatigue stress concentration factor is lower than the static stress concentration factor or theoretical stress concentration factor. And that is the experimental data. We will try to understand why that happens. What happens is, for a dynamic loading scenario, we need to modify the theoretical stress concentration factor based on something called notch sensitivity of the material. Right? What is notch sensitivity? If you have a ductile materials, they are less notch sensitive. Brittle materials are more notch sensitive. That means ductile materials, if you have a notch, then that is actually going to delay the fatigue failure of the material. That is what we mean by notch sensitivity. So if you look at this parameter called notch sensitivity, Q, as a function of notch radius, as you reduce the notch radius, the notch sensitivity reduces. As you increase the notch radius, right, the notch sensitivity increases. That is what reduction of notch radius decreases the notch sensitivity. So this is a very useful concept in understanding, in applying a fatigue stress concentration factor. If a notch has its maximum possible effect, then Kf will become equal to Kt. Otherwise, it is not. The value of Q, that is notch sensitivity, decreases from unity if Kf is less than Kt. That means with Q equal to 0, for Kf equal to 1, that means there is no notch effect. If you have a material, you have the Q increases with the notch radius, as well as it increases with the ultimate strength of the material. So we need to understand. So now what is the relation between the notch sensitivity, fatigue stress concentration factor and theoretical stress concentration factor. This is the relation between that. The Notch fatigue stress concentration factor is given by 1 plus Q times KT minus 1. If Q is equal to 1, then fatigue stress concentration factor is equal to theoretical stress concentration factor. Right? That means there is no notch sensitivity at all. While your fatigue stress concentration factor is equal to theoretical stress concentration factor when Q equal to 1. When Q equal to 0, then Kf will be equal to 1. That means Q, there is no notch sensitivity. When Q equal to 0, then fatigue stress concentration factor is 1. That means there is no effect of having a notch there, which is when Q equal to 1 means here, somewhere here, right? Very high large radius. Okay. So now once having calculated your Kf, your actual stress will be Kf times nominal stress. So by looking at this guy, you can always say that what is the value of Q? Q varies between 0 and 1. The minimum value of Q is 0 and the maximum value of Q is 1. If Q is equal to 0, Kf equal to 1. That means nominal stress and actual stress are same. But if Q is equal to 1, then KT is usually always greater than 1. So this means this value will be something depending upon the value, and Q becomes Q being less than 1, Kf will always be less than KT. You can see from this relation. And now how do you compute Q? How do you get Q? In order to find out fatigue stress concentration factor, if you know theoretical stress concentration factor, you need to compute notch sensitivity Q. This notch sensitivity Q depends on material property and the notch geometry. This A is not crack length. There is no crack here. Here, this is what we call Neuber's constant, which depends on the ultimate strength of the material. So the Neuber's constant depends on the ultimate strength of the material and the way the material is made. Using that, you can plug in the notch radius and compute Q, or in the data handbooks, you can directly obtain Q from this Q versus notch radius plots for different ultimate strengths. And look at this graph and then find out Q. Once you have Q, you plug in there and then you get the fatigue stress concentration. Okay? And then you see that if you have a material and if you change the notch radius, as we know, theoretical stress concentration factor increases as you continue to reduce the notch radius, meaning the notch becomes sharper and sharper. Whereas fatigue stress concentration factor, sort of as you reduce the notch radius, here you are reducing the notch radius, right? If you are reducing the notch radius, what happens? The Q approaches a constant value, right? You please look at that. And that means your fatigue stress concentration factor sort of saturates as you reduce the notch radius. And you will realize that for a very large notch radius, Kf and KT are same. But for small notch radius, because very large notch radius, if you look at this fellow, if you have very large notch radius, Q is becoming 1. If Q is becoming 1, Kf is equal to KT. Right? That is why for a very large notch radius, Kf and KT are same. But when you reduce the notch radius, KT becomes larger and larger, but Kf sort of saturates. Why is that? The reason for that is if your notch radius is smaller and smaller, then the stress concentration factor here is going to be larger, and then ahead of the notch tip, the stress goes to very high number. That means there will be plastic deformation ahead of the notch. If there is plastic deformation, then your fatigue crack cannot grow. That means notch becomes blunter and blunter because you will have local stress reaching to the plastic, causing the plastic deformation of the material. So if you look at this particular figure, if you know KT times stress amplitude should give you this stress, but the reality is that ahead of the crack tip, you will have some plastic zone. Because there is some plastic zone, depending upon the size of the plastic zone. The actual effective stress before the material given by Kf will be sigma E by Sa. Right? This is sigma E is what? Average sigma Y as x is equal to 0 at such that x tends to delta. So that means if you take the average area under this, depending upon the size of the plastic zone, that gives you the sigma E, which will be smaller than Kt times Sa. And that is the reason, because there is a fatigue stress concentration factor, you cannot take a point function. You have to choose certain material and you need to average the stress over that region depending upon the size of the plastic zone, and that reduces the peak stress, right? So why Kf is smaller than Kt? There are two reasons. One is process zone size effect. A lower value of Kf is possibly due to discrete microstructures such as crystal grains having the effect of equalizing the stress over a small domain, because you have a finite size and the peak stress is going to be equalized over a small domain, the delta. And another reason is the crack growth effects. So for example, let us say you have a crack that may start quickly at a notch very fast because the stress is very high because of the nominal stress. And now if you have a smooth member that is subjected to Kt, theoretical stress concentration times applied stress, yes, so that both the notched member and smooth member gives the same fatigue level. Let us assume that. Then if you have a notched member, the crack grows into a region of rapidly decreasing stress, whereas for smooth member it does not happen. As a result, what you should have is the notched member ahead of the notch rapidly decreases, while for a smooth member the stress does not decrease rapidly. So that is why you need more number of cycles for failure in a notched member compared to the virgin with unnotched member. That is the reason why your Kf is less than Kt. It is basically the plastic deformation ahead of the crack tip. Okay. So I think I'll stop here. These slides are available. I would like you to read. It is not easy to follow immediately unless you carefully read these slides and understand. And by next class, you should be clear why Kf is smaller than Kt. If not, I will reiterate in the next class. Is that okay?
Yes, sir. Sure.
Yeah.
Yes, sir.
Okay. All right. We will talk about, once this is done, we will talk about Paris law. We will solve some problems with notches, and then we will talk about Paris law, and then we will move on to strain life approach, because we have studied so far stress life approach, high cycle fatigue. Later we will start talking about strain life approach. Okay. I think with that I'll stop here and we'll meet again next week. Yeah.
Professor.
I think we have a special class, a compensation class on 3rd December.
Yes, sir. Yes, sir. 3rd December, special class. Sir, before that, any other class required, sir, for us?
Not required, because 1st and 2nd December we will have anyway our class.
Okay. So our last class will be on 9th of December, sir. That is the last class.
I think the last class will be 9th December. You will have 1st, 2nd, 3rd, 8, 9, 10. Yeah.
Okay.
8, 9. 9th will be the last class, and the exam is on 20th.
Yes, sir. Yes, sir. Sir, just now we received a mail from code office that we are joining a separate WhatsApp group.
No, I asked them to create, because if I have to quickly communicate something to all the
Right.
class, I can
Okay, sir.
do it that. Yeah.
Yeah, sir. Thank you, sir.
Yeah. Yeah.
Thank you.
Okay.
Thank you, sir. Thank you so much.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.